Sections 9.2 and 9.3 are both about differences in means, but there are two options. So 9.2 covers independent samples, so this first option right here, and then 9.3 will be paired samples. So independent samples, that is, like it says there, it's a default case. So in general, unless there's something that would tell you that you had paired samples, you would do this. So this ends up being the more common scenario where there's no natural connection between the two samples. It's just two completely separate groups. So you have group number one from population number one, group number two that comes from population number two, and that's what your samples are. So as far as inference goes, when we did this with a single mean, we said as long as the sample size was at least 30, that would be big enough for the central limit theorem. Here, it's that you need both of them. So as long as both sample sizes are at least 30, then you can apply the central limit theorem. And then if one of them or both of them end up being a little bit too small, then you would do what you would do for a single mean. So for that population, like let's say hypothetically, sample one's too small, but sample two is big enough. Then sample two, basically we're good to go, but then sample one, we would have to take a look at a histogram of the sample, and we'd want to make sure that at least it was symmetric with a single peak, right? That it looked as bell-shaped as you could get it, even if the sample size comes up a little short, even if it's 26 or something. All right, so as long as we feel comfortable applying the central limit theorem, then just like when we did things with a single mean, we're going to use the t-distribution, but the degrees of freedom is going to be kind of an ordeal, because then you think, okay, well, what is the sample size minus 1 when you have two totally different samples? So what our book does is it uses the minimum of n1 minus 1 and n2 minus 1, at least for the stuff that's done by hand. It's a little conservative. It'll give you a value that's a little bit smaller than the other estimates, but if you're getting a value that's a little bit smaller, then you get the thicker tails, so you'll get an interval that's a little wider than necessary, which is okay. The other way around wouldn't be, right? If you got an interval that was too thin, for 95% confidence, that would be a problem. If it's too wide, that would mean that the interval actually has a higher confidence level than the one you were aiming for, so that's great, right? There's nothing wrong with that. The alternative to using the minimum of n1 minus 1 and n2 minus 1 is this thing right here, which is called the Welch-Satterthwaite equation, or a lot of times that's just called Satterthwaites approximation for the degrees of freedom. Basically, if you were going to do that by hand, it would turn into an exercise in making sure you have enough right parentheses if you try to put that all into your calculator. That's kind of what that is. Because it's not like it's hard. There are just a lot of individual little pieces in it. And actually, if you have StatCrunch do all the computation for you, it will use the Welch-Satterthwaite equation to get the degrees of freedom. So it'll give you, I guess, a more precise approximation than the minimum of n1 minus 1 and n2 minus 1. All right, then when you compute either a confidence interval or a test statistic, that's what the standard error would look like. And if you look at that, it looks kind of like what you would get if you combined the two individual standard errors. So kind of like what happened with a proportion, right? We got more things going on underneath the radical. Basically, we have twice as much stuff because we have to account for the variability in the first sample and in the second sample, right? So all that together, we get twice as much as what we would have if it was just for a single sample instead of two. All right, so then the confidence interval. All right, so the point estimate. The natural point estimate for mu1 would be x1 bar, and the natural point estimate for mu2 would be x2 bar, right? Just in general, whatever group you're looking at, your best point estimate for its population mean is going to be the sample mean. So therefore, I guess ultimately, the best point estimate for the difference of population means will be the difference in sample means. You would use the t-distribution to get the critical value, and then there's the standard error, so altogether, there's the confidence interval formula down at the bottom of that section. Then for hypothesis testing, just like with proportions, the null is that the two population means are going to be the same. And then most often the alternative is that they're different. So where you would just have a not equal to, but you could have a one-sided alternative. It is possible. So let's see. Then the test statistics. So the delta 0, I kind of generalize that again. That's going to be 0 if you're using this null hypothesis here, which we're going to. It's never going to change from that. It's always going to be that for a difference in means, at least with independent samples. So then the delta 0 is just 0, and so that's why you end up with this test statistic right here, which is the one that we're actually going to do in the parts where I have it written out by hand. So how do you do this in StatCrunch? Right? I mean, I guess that's probably the natural question. It's pretty close to where you would go for like a confidence interval or a hypothesis test for a single mean. It's just that you pick 2 sample instead of 1 sample. So I can show you. If we go into StatCrunch, if I go to Stat and then T-Stats, 2 sample this time, and then sometimes, like it will come up, I think, at least once or twice where you'll have to do it with data, and I do have an example of that. But the first example we're going to do is with summary, so I'll set it up for that first. All right, so there's our first example where we have 2 samples full of soil specimens. Right, so like it says there, chemical composition of soil is going to change the farther down you go. So there's sample number 1 where we have 50 soil specimens at a depth of 100 centimeters. And then sample number 2, we've got 48 specimens taken at a depth of 250 centimeters. All right, and then we have our summary values. We've got our x1 bar and s1, x2 bar and s2. So from our first sample, I guess this would be for 100 centimeters. I guess we're going to call that sample 1 since it shows up first. Right, like it shows up first in the wording. Then we've got that x1 bar is going to be 88.5. S1 is 49.4. And then N1, the sample size was 50. Then at 250 centimeters, we've got that x2 bar is 110.6. We've got that S2 is 51.5. And we've got that N2 is 48. All right, then if we go to StatCrunch, then we just have to put in the sample values for this first sample, then the second sample. So that's what we're going to do. So first sample was 88.5, 49.4, and 50, and then 110.6, 51.5, and 48. Then we want a confidence interval, and we're looking for a 95% confidence interval, so I don't have to change the level. And if I click on compute, there we go. We've got our endpoints, I guess, at 3 places with each, negative 42.351 and then negative 1.849. All right, so then from StatCrunch, we're going to get that our 95% confidence interval is going to be from negative 42.351 to negative 1.849. All right, so then there's the follow-up question at this confidence level. Would it be reasonable to conclude that the mean concentration of NO3 at a depth of 100 centimeters is different than that at 250 centimeters on the farm? Well, the number that would basically equate to the means being the same would be 0, right? Because if it's the difference of means, if you get 0, then you'd say, well, then they must have been the same. So 0 is not in that interval because the whole interval is negative if both endpoints are negative. So this one would be yes, it's reasonable to conclude that there's a difference since 0 is not in the interval. So we can say yes. since 0 is not contained in the confidence interval. So whole interval is negative, you can conclude that there's a difference. Whole interval is positive, you can conclude that there's a difference. But if 0 is in there, so I guess that would be one negative endpoint, one positive endpoint, then you can't. So works the same way that it did for proportions, right? Basically, if you're looking for evidence of a difference, you want 0 to not be in the interval. All right, if you were going to do it by hand, this is what it would look like. You'd have to go get that critical value. So I guess there, and this is probably worth doing in StatCrunch, what you would have to do, and I guess I need to go back here for a second, because you can see the sample sizes here, one's 50 and one's 48. You'd have to use the minimum of n1 minus 1 and n2 minus 1, so minimum of 49 and 47, which is 47, like how it says 47 df in the parentheses up there. But then if you were going to do this in StatCrunch, you'd have to use the T calculator and put in 47 degrees of freedom. And then I guess you would need I guess you could do it as a between and just say you want your between to be 0.95, like that. And there's the 2.0117 critical value, and that's exactly what I've got right up there. So then once you get that, it ends up just being a lot of algebra that you would probably have your calculator do. Notice that the algebra is actually not as bad here as it is for a proportion, because the root isn't quite as complicated, right? There's still a big root, but what's under the root, there's not as much going on, right? So if you were going to do it by hand, this one actually wouldn't be quite as bad. And then eventually you end up simplifying it down to the endpoints. The endpoints here are a little bit different. They're actually a little farther out. Because in the old ones, like if I just kind of scroll up and back down, oh look, I can get them on the screen at the same time. All right, the ones that are in maroon up toward the top, right, it's a little bit different than what we've got down here. The reason for that is mostly just because it's a different value for the degrees of freedom. So there's that. I mean, I guess there's a little bit of rounding with the margin of error, but I don't think that would cause much of an issue. Most of it is that, different approximations of the degrees of freedom, because here we're using 47, and then StatCrunch uses the Welch-Satterthwaite equation, or Satterthwaites approximation, whatever you want to call that thing. It works out to be about 95. And I guess if you look at that and go, that's not too far away from n1 plus n2 minus 2. No, it's not, right? It's a little bit smaller because n1 plus n2 minus 2 would be 96. So usually the Satterthwaite ends up around that. It's usually a little bit less than n1 plus n2 minus 2. But that does also kind of depend on what the sample standard deviations are. If those are really far apart, then occasionally you get things that are a little bit different. But yeah, I mean, there are slight differences, but the homework would be set up to accept either one. Like the tolerance ought to be wide enough to where either one of them would be all right. Then, hypothesis testing. So, based on information from the Rocky Mountain News, we have a random sample of 40 winter days in Denver, sample mean pollution index of 43, standard deviation of 21. For Inglewood, which is a Denver suburb, we also have a sample with a sample mean, sample standard deviation. And the only direction that would really make sense here, just considering where you think, well, Denver is a big city, Inglewood is a suburb that's not really that big, that you would think the population density in Denver is probably going to be higher, and you'd think, you know, there's going to be more traffic, probably more pollution, right? Like that would make sense. So we're just going to look at that one direction. We want to see if the mean pollution index in Denver is higher in the winter. So if 1 is Denver and 2 is Inglewood, then let's see, I guess we'll have our null that we'll back solve for, And the alternative is that we're looking for higher in Denver. So if 1 is Denver, then we're looking for evidence that mu1 is greater than mu2. And then the null would just be mu1 equals mu2, right? Looks like the alternative, but with an equal sign in it. All right, then we're going to use StatCrunch to get the p-value. So let's see. Then for Denver, we've got x1 bar equals, let's see, 43. And then S1 equals 21. And then the sample size is 40. And then for Inglewood, we've got that x2 bar is 36. S2 is 23. And then N2 is 44. And then we can go to StatCrunch and do it. So let's see. We go to StatCrunch. That's not what I want. I want stat, tstats, to sample with summary again, right? Because we got x bars and s's. We don't have raw data. All right. So sample 1 is Denver. So I guess we're going Denver first. 43, 21, and 40. And then sample 2 would be Inglewood. So 36, 23, 44. And then for the hypothesis test, it was supposed to be looking for evidence of higher in Denver. So I need a greater than, right? Mu1 greater than mu2 is the same as mu1 minus mu2 greater than 0. And then if I compute, there's my p-value of 0.0743. Okay. So with StatCrunch, what we got was a p-value of 0.0743, and then we're using the typical 5% level of significance. So for part C, what conclusion are we going to end up with? 0.0743 is bigger than 0.05. So that means that the p-value is bigger than alpha, and that's the case where the null should not be rejected. Right? We don't have enough evidence to reject it, so the null should not be rejected. All right, and so then as far as the formal conclusion goes, something like that there is not enough evidence or there is insufficient evidence to conclude what's in the alternative. So insufficient evidence to conclude that, and I guess in words it would be that the mean pollution index of Denver is greater than the mean pollution index of Inglewood in the winter. So the mean pollution index of Denver is greater than that of Inglewood in the winter. All right. And then I did do this by hand. I already have it written in. If you have the test statistic, and then you'd have to use the degrees of freedom. I guess you wouldn't have to. You could use the Satterthwaite equation if you wanted to. But if you do it the easier way to do it by hand, do the minimum of n1 minus 1 and n2 minus 1, you're going to get 39. And that is why the p-value is slightly different. Right? Here it's 0.764, and what we got from StatCrunch was 0.743. So that slight difference is due to a different value for the degrees of freedom. And I mean, we still end up with the same conclusion anyway, right? Like the p-value is not that different. But this would be what the p-value would be, right? It's a greater than, so it's just going to be a right tail bounded by the test statistic when you're using a t-distribution with 39 degrees of freedom. All right, the other option would be, what if you were going to use a confidence interval? So for that last example, what if we were going to use a confidence interval instead of a p-value? So what would be the correct confidence level? I just wanted to bring in another one of these because This is a one-sided alternative, so you could do it with a confidence interval, but the adjustment that you have to make is a little unorthodox. So this did show up with proportions, but I think it's worth bringing this up again. So the null was mu1 equals mu2, and the alternative was that mu1 is greater than mu2. And then it was with the usual alpha of 0.05. So then you would need 0.05 in the right tail for a rejection region or for where your critical value should be, I guess depending on how you want to look at that, which would mean that if you need a 0.05 in the right tail, you should be using a 90% confidence interval, right? Because I think I can draw a little one up here, I think. Because if you're getting a 90% confidence interval, then in the middle, you're going to have the 0.9, and then left over, you'd have half of 0.1 in each tail, right? And we're supposed to have 0.05 in the right tail, so this would be the thing that works. So we want that 0.9 or 90%. And what it ends up being, since I did go ahead and figure it out, the 90% confidence interval would be from negative 0.987 to positive 14.987, which I guess you could do if you wanted to get it in StatCrunch. Let's see. So the data is already in here. You just have to go to Options, Edit, and say, now I want a confidence interval, but I want a 90% confidence interval. And there it is, right? If you look at those endpoints, it's negative 0.987, positive 14.987. All right. So the big thing is getting the correct confidence level, because this is the weird case where it's a one-sided alternative where then 1 minus 2 alpha is actually the right thing. Whereas if you have a two-sided alternative, if you have a not equal to in your alternative hypothesis, then 1 minus alpha would be the thing that you want. All right, the last example, because I wanted to have one that used raw data. And that's why it says data in CSV file. So there is a grandstrand.csv file that's right next to these notes on Moodle. And the reason I used a CSV is because they have less formatting. So they always copy in directly. So like if you're just going to copy and paste, it always works. That's why it's that rather than like an Excel spreadsheet. Plus, a CSV file will work even if you don't have Excel. So the Grand Strand Family Medical Center is specifically set up to treat minor medical emergencies for visitors to the Myrtle Beach area. There are two facilities, one in Little River, one in Murrells Inlet, and the Quality Assurance Department wants to compare mean waiting times for patients at the two locations. All right, sounds like a difference in means with independent samples. And then that Grand Strand file, I actually have it. It's right here. I don't think it's too long. No, I mean, like, if you had to type that in by hand, it wouldn't take forever, but it would take a few minutes. It would take a few minutes that you would probably rather not spend typing in a bunch of numbers. So we're going to use that this time. And let's see. So what we're going to do is we just want to see if there's a difference. So not specifically that one is longer than the other. So I just wrote this with 1s and 2s, and I said if 1 is Little River, and then 2 is going to be Murrells, 2 L's? Yeah, Murrells Inlet. Then what we've got is a null that mu1 equals mu2 versus an alternative that mu1 is not equal to mu2. And then we just have to go get our p-value. All right. Well, if we use StatCrunch for this, I'm just going to copy these right here. So I'm just going to highlight those, Control C, and then in here, and I'm going to paste into the heading, because then that way Little River and Merle's Inlet show up as the heading rather than as like the first row of data. And then this time, if I go to stat, then tstats, and then to sample, now I want to go to with data. So I go to with data, and then it'll ask me where the data is, and I say sample 1 is in the column called Little River, and then sample 2 is in the column called Merle's Inlet. And then we are going to do a hypothesis test, and it's two-sided, so we're good to go here. And compute. All right. Then there's our p-value of 0.0125. All right. So what we got from StatCrunch is that the p-value is 0.0125. All right, now we just have to make a decision if we should reject the null or not. It's the usual alpha, right? It's alpha's 0.05, so our p-value is 0.0125. That is less than 0.05. So the p-value is going to be less than alpha, and so that means that the null should be rejected. All right, so it's a little bit different when you have the raw data, but if you're given that raw data, and I think in the homework, there's something you can click on toward the upper right of where the data is, where you can copy it, and then just paste it into StatCrunch, and then if you pick with data instead of with summary, it'll just ask you what columns have your two samples. And you just have to specify this column and then this other column, and then from there it'll know what to do. So it's a little bit different, but I think once you've done it once or twice, it doesn't take too long to get the hang of it.